the modern Newton's laws of motion. This, which I said, the law of inertia, this was the founding base of Newton's laws of motion, and it is sometimes it is also referred to as Newton's first law. So we will discuss here Newton's first law. So that's why Galileo is treated as the father of modern. That's why Galileo is treated as the father of modern physics, because the founding base of Newton's laws was the Galileo, Newton's laws of motion. Newton's laws of motion. What was the first law? There were three laws actually: first law, second law, and third law. You might be well aware about those very laws, but I will give a brief concept about those very laws. So first law, which is also called as the law of inertia, first law of motion. First law of motion says that every body, I will write it down like this: every body continues to be in its state of rest, one thing, or of uniform motion, These are the two things. But according to Galileo, these two things, rest and uniform motion, these are equivalent to each other. Not in that case that rest is equal to the motion. No, that's not the case. He said that as long as external force is not applied, both of these conditions are not changed. So this also needs to change the state of rest. It also needs force, external force, and uniform motion. This also needs some external force. So the first law of motion, Newton quoted that every body continues to be in a state of rest or of uniform motion along a straight line, or in a straight line. In a straight line, because straight line motion is possessing the uniform motion. Straight line. Then in that case, or of uniform motion along a straight line, unless compelled by some external force, to act otherwise. For example, if the body is at rest, then if external force is applied to it, if it is first at rest, okay, if external force is applied to it, it will come in motion with some velocity v. So its state is changed. First, it will possess the property of inertia. It will remain at rest. Now, since the external force is applied to it, it will possess some velocity. So its velocity changed from 0 to v, and change in the velocity is called as the acceleration. Okay, so force brings in acceleration. This is the key word for the second law of motion. Keep that also in mind. Okay, similarly, if the body is moving with some velocity v, here it is also v, but here applying force, if force is applied in this direction, or say in this direction, opposite to the velocity of the motion. Okay, so in that case, first it was moving with the velocity of v, but here it comes to rest. So velocity comes to halt. That's v equal to 0. So velocity is again changed from v to 0. So that means again acceleration. In this case, it's retardation. So that means again the acceleration is observed, whether in the negative direction or the positive direction. That is the case here. It is the case of retardation. So acceleration is again observed. So this acceleration is again caused by some external force. Okay, so that means Newton said that every body, it continues to remain in the velocity in the uniform motion. It continues to remain in the at the state of rest until and unless some external force, some external force here is acted onto it to act otherwise. Okay, this is the only condition that a body can change its state, and this was totally opposite to that for that theory which was given by Aristotle. Aristotle said that no, to keep this body in uniform motion we need an external force. Galileo said no, you are wrong. It is external force required to change the uniform motion, not to keep the body in uniform motion. If external the body comes to which you think, they said to Aristotle that you think that the bodies are tired. It's not the bodies becoming the something like human beings. No, it's actually the ground which is providing the friction. Okay, so it is this very frictional force which is making the bodies to come in rest. So here external force acts as the friction acts as the external force. Okay, so first the body was moving with the uniform motion, then the frictional force is applied to it, it comes to rest. It is not the body is getting tired, no. Similarly, if the body is at rest, to keep this body in motion, we need some external force. In all the cases, whether the body is at rest or of uniform motion, to change the inertia of this very body, we need some external force. Okay, this was the first law. So every body tries to remain in its original state, unless and until compelled by some other external force to act otherwise. This was the Newton's first law. So we said that the acceleration here is caused by some external force. So we can say that, but there is a problem. Suppose a body here, if a force is acted onto it like this, it will come, for example, it's at rest, it will come in motion. But if another same force is acted in the opposite direction, one force is acting, F1 is like this, F2 is like this, and both cancel out each other, what will be the end result? This body will stay in the state of rest, because both of these forces are cancelling out each other. Fine. So that means if the total sum of the external forces, say for example here another force is acted onto it, here another, this cancels out this cancels out this, another force like this, another force like this, these two cancel, another force like this, but here another force is like this cancels this very thing. So that means the sum of the total external forces, that is the resultant net external forces. Resultant are the net external forces. If net external forces onto a body is 0, they are cancelling out each other. Similarly, in case of the moving bodies, if the total forces acting onto the bodies are cancelling out each other, that is the net resultant force is external force, I am saying, is 0. That means there will be no change in its original state. That means no acceleration will be brought in. Okay, you saw here that acceleration is brought in by what? By some external force. But here force is applied, but forces are cancelling out each other. That is the net acceleration, net external force is 0. That means if a body is observing a net force of 0, external force 0, that means there will be no acceleration. Or in other words, if a body is not accelerated, at all, if it is moving in a uniform motion with a uniform velocity, that means there will be no acceleration, and that in turn means that no external force is acting onto it. Or this is equivalent to saying that the total forces, if there are more than one force, more than two forces, then the resultant of those very forces is actually 0. Because it is as if the total forces are acting onto it. It is as if that no force is acting onto this body. So that's because no acceleration is observed onto this. Like I can elaborate this very concept in another example.